Hi, Science 30s. So this is going to be me kind of walking you through a portion of the Explore Learning Gizmos that I've sent you and a little bit about the assignment. But know that this assignment sometimes things do come up. So I'm going to try to address a couple of things that I find are pretty frequently seen. So I sent you, or I will send you, like a username and password. It's usually like your first and last initial and then a whole bunch of garbage letters and then or garbage numbers. I'm just going to log in a test one just so I can see what you guys can see. Oh, there's my name. So I think right now I threw three in quickly. But there's lots of other little applications that are actually kind of fun for physics and also for a ton of other units. So if there's anything you're interested in, let me know and I can pull them up. So the one that you're going to do the assignment on is advanced circuits. But I was kind of thinking that you might need to play around a little bit with the circuits one first. So I added that in, and I'm not going to there is an assignment for it. I have it pulled up right here just to kind of guide us through a couple of things. So I think we'll do a couple of the things in circuits together, and then I'll go a little bit through the advanced circuit stuff. So if you click on it, it opens up and it should look like this. Looks like kind of a pegboard there, so little connections. And then we have a whole bunch of things that we can use. This isn't the one. Did I click the right one? I thought it looked different than this. Hang on, I'm going to pause this because this isn't the one. Okay, I sorted it out. I needed the one called Circuit Builder. I added that to all of you guys. So now I'm logged in mine. So there is one called Circuits, and you can look through that too. That might actually be helpful as well, but I just want to look through this Circuit Builder just so you get an idea of a couple of things. So there's some prior knowledge ones, but it says using the standard components, so the stuff that's up here, try to get a bulb to light up. So if I just throw a bulb right here, no lights. And then if I'm like, okay, I need a closed loop. All right, let's make a closed loop. No lights, not good. Okay, what if I put a switch and then I turn it off and I turn it back on again? No lights. All right, so now what if I had a battery? So a battery cell, whatever you want to call it. Well, what if I do that? Ah, look at that. I've lit up my bulb. So that's just a couple of the components. And so we can, I don't remember. Oh, I think you have to pull things off. You can't throw things on top of each other. So just kind of play around with it and see what happens. And if I throw another one, oh, that's a brighter light. I think that comes up later. So a circuit is a path containing easily movable charges. When the bulb lights up, negatively charged particles called electrons are flowing through the wire and bulb. This flow is called current. So trying to light up the bulb with the smallest number of components. So I probably didn't need these two wires. I could probably check them up here. I really don't actually need this switch. I could have just had a wire there. But I guess I have it in there. So based on what you have seen, what must be true for a circuit to light up a bulb? So we need to have a closed loop, and we know that we need to have something that's generating those, contains a source of electrical potential energy. So something that's supplying those electrons. So get the gizmo ready. Activity, closing a circuit. Okay, so this one, it says set it up like they have it. Well, mine looks a little different right now. So you should just have an open circuit shown above. So there's a little diagram here. The gap to the left prevents the flow of charges. So this is a problem. We don't have a closed loop so that it is not able to flow. So no, yes, we have a negative terminal, but it's not hooked up to that positive terminal. So those electrons aren't flowing because they have nowhere to go. So we have insulators versus conductors. Conductors are materials with easily movable charges, allowing current to occur. Insulators do not have easily movable charges, so current is not produced. Look at the 9 materials on the lower left. Which do you think are conductors? Which are insulators? So we have pencil lead, we have glass, we have iron, we have silver, we have wood, we have brass, we have plastic, we have copper, and we have yarn. So just give it a thought right now. We talked about some of this already, is which of these will conduct. So I'll go through them just really quickly. So looking at conductors versus non-conductors. So this is pencil lead. It lights up. This is glass. It does not light up. Not a good conductor. Iron lights up. I just want to see that one versus this one. Looks about the same. Silver, it lights up. Wood does not light up. Not a good conductor. Brass lights up. Plastic, nothing. Copper, yeah. And yarn, nothing. So what we could also do, so when I have something that is conducting, so I have a piece of iron, is we can also show the current. So again, I want to show the electron flow. You would have heard probably somewhere in those crash course videos, she talks about the conventional current versus the electron flow. It's an old, ridiculous way based on observations that they made appropriately in the time, but current is not the direction of the conventional current, opposing that. So if we were looking at the electrons, it looks like these little blue dots are representing electrons that are blooping out of this negative terminal. They're flowing this way through this conductor, the iron conductor that we chose, towards the positive terminal. So those are your conductors and insulators. So the next one, okay, so that would be, oh, it's just closing a circuit was all that one is. When you're playing with these, I'm just trying to show you some of the ways to use it. So you see that I pick stuff up and drag it. You can throw stuff off wherever you want. You don't have to like put it back on the light bulb. If you have a lot on there and you want to get rid of it, you just press clear. So now it's asking us to look at a series circuit, which we kind of already did. So check that show current is on, build the circuit to the right. So whenever it's asking you to do that, just pop on stuff, put that there. I need a couple of wires here. Build battery there. A wire and a light bulb. So you can see right now, before I put the light bulb down, there is no current flowing. So see, it says show current, and as soon as since my switch is on right now, if it was off, it would not be showing that, but that shows that now that I have a closed loop, current is able to flow. So notice how brightly the bulb is lit and how much current there is. Now start replacing wire segments with light bulbs. Okay. Oop. I guess I can just drop over. So hopefully you're kind of seeing that as I replace those segments, the lights are getting less bright. So I'll change them back to wire. It changes as you add more bulbs. And again, that's related to kind of the properties we talked about with series circuits. The voltage, the same amount of current will go through each part of the series circuit, but again, the voltage will be based on the resistance, and we know that those light bulbs will have an internal resistance. This next one is saying, do all the bulbs have the same brightness? So when I add a whole bunch more on, you see that like the first light bulb isn't the brightest and then it gets less bright. Those are all the same brightness. So look at the current arrows in each part of the circuit. Are there any parts of the circuit that have more current? No, current is going to be constant throughout a series circuit. It says now remove a light bulb, leaving a gap. So this is similar to what your assignments are going to look like. So it gives you an instruction and you just have to kind of follow along. What happens to the remaining bulbs? Oh, well, we broke the series circuit. So now we do not have any closed loop for which the electrons can flow. So now all those light bulbs are off. So this is what I was saying with Christmas lights. If you have lights that are connected in series and one bulb blows out, the whole line goes out. And then you don't know which one was broken, right? So build another series circuit with several light bulbs, 1.5 volts. Okay, so I think what this one's asking, so several light bulbs. So this is the 9-volt battery. What if I replaced it with a 1.5 volt instead? So you can see, I'll do that again if you weren't watching. So look at that current, and then if I hook this, I guess I have it the wrong direction. There we go. So look at how the light bulbs have changed. Look at that flow of current. And now if I replace, I guess we do it that way. So if I replaced it, you saw the lights got a little bit brighter and those little dots started moving a little bit faster. I'm not going to go through everything, but let's do a parallel circuit now. Wire, battery, light bulb. Ooh, that's happily flowing. I guess I could have, let's turn that off. Boom. Boom. Okay. So build the circuit to the right. In a parallel circuit, there are more than one path that current can take. So current can go around here and through, or current can go around the long loop and back. So it says turn the switch to on, which allows charges to flow through the circuit. Notice how brightly each bulb is lit and how much charge is flowing through each part of the wire. 2 bulbs equally bright? Yeah, they're pretty happy. Oh, add 2 more bulbs. Well, I can only fit 1 more because I didn't read ahead. I guess I can move some stuff. We'll get by. So as I add 1 bulb, so pay attention to the current. I'll let that sit for a second. Pay attention to the current and pay attention to the brightness of the bulbs. So, no change. Sorry, I hear weird music. Do I have something playing? Nope, I'm just losing it, guys. So we see that nothing changed. So the brightness didn't change. If I pull out a bulb, even if it's one in the middle, and throw it over here, nothing happens with the other 2. So when a bulb blows in a series of light bulbs that are connected in parallel, it doesn't impact the other bulbs. So how did the parallel circuit respond differently than a series? When you added bulbs, there was no difference in the brightness or in the current, and when you removed bulbs, it didn't impact anything. So replace. Okay, so replace the bulb with a wire, so the one that I took out already. It says replace it with a wire. And so it says short circuit detected the red loop. And so this situation is called the short circuit. So the red arrows indicate an enormous current. This is very dangerous because the current will heat up the wire and can even start a fire. So without something like a light bulb that has an internal resistance, that is too much current flowing through that particular wire. And so again, that wire can heat up and catch on fire. That's not so good. So if when you're playing around you get a short circuit, you need a resistor, like a light bulb, or you can put a fuse on. Okay, they have a fuse question. So it says apply or short circuits can be avoided using fuses, and fuses are devices that melt if they're too hot. So if there's too much current coming through them, it still will heat up, and what happens is the internal portions of it melt, and as that melts, that actually creates a break in the loop, and therefore no more current will flow through it. So if we put a fuse there, So if I put a fuse there, what you maybe didn't see, because I did it very quickly, is if I drop a fuse on, so the fuse should look like this when it's sitting, but I drop it on and it actually very quickly heats up, melts, and closes or opens that loop up that now current isn't flowing through there. So current just flows through our two resistors or our two light bulbs. And so um, we used to have fuses in our homes. Maybe if you have an old home that hasn't had upgrades, you still will have fuses. And so when you had a problem with the amount of current coming in, so if you were using too many devices and drawing too much, you would blow the fuse, is how you would say it, and it would break and you would have to replace it because it breaks irreversibly. Now what we have is we have circuit breakers. So you've probably seen in your house somewhere a big kind of gray panel that if you open it up, there's a whole bunch of switches on there, and you can flip the switches back and forth. And usually if you have a problem with the amount of current running through, if you're running too many appliances or something like that and pulling too much current through, what will happen is that switch will flip automatically and again open that loop, creating a problem where current can't flow through it, and that means that those wires aren't heating up. But what you do is you go and you flip the switch back and you make a change as to how many things you have plugged in. So we usually use circuit breakers now. I know my home is pretty old. It was built in the 50s and we have a full circuit panel. I don't know that any homes would still have fuses on them, but it's kind of a good reflection for this. Oh my god, how long is this lesson going to be? Wow! Okay, so that's the circuit builder one. That's the end of that. So the next one, you can go through the app that's called Circuits. Let's see. Oh no, did it sign me out again? Doof. Okay, my homepage. I don't know why you guys had Circuits. You can, if there's one called Circuits as well, there will be kind of an applet and then the assignment. So Advanced Circuits is the one that I want you guys doing the assignment for, and you do have an assignment in the package that I gave you guys at the beginning. So it will look, if you for some reason don't, I think you can click on yours and you can open the assignment. So Student Exploration, Advanced Circuits. This will be your assignment. And you see it's not short, but you're going to do a lot of playing around. And if you get stuck on a question, just bop onto the next and send me an email and we can pop onto a Google Meet and kind of go through it together. But don't think like if question 2 stumps you, don't be like, I can't do any of it. You're probably just stuck on a portion of the question. So I'll go through some of the assignments. So you see that the circuit thing looks a little bit different. So you have 2 different fuses. So this will blow at a fuse, I believe, or at a current of 0.15 amps. This one blows at 0.3 amps. We have different resistors. So 10, 20, 100, and 200 ohms. And you see that we don't have all those metals at the bottom. So we don't have whatever it was, copper and plastic and those sorts of things. So you don't need it for this one. But a couple things that are different. So the battery, so last time you had a 1.5 volt and a 9 volt. So the battery, if you need it, you can change the voltage of the battery. So you can have really high voltage. I think sometimes it'll tell you which voltage to use. So just make sure you change that as you need. I think you click on the battery if you have more than one in. If you also, yeah, you see if I click the battery, it also switches which end is the positive or negative terminal. I guess I'm kind of dragging it there. And then we have the meter. So when you need a voltmeter, an ammeter, and an ohm meter, this is where you put them. And so you'll line them up accordingly as you need. So just looking through the assignment, I'm not going to go through every question because I want you guys to do a little bit of an investigation on it. So prior knowledge questions. So what is the mathematical relationship between current, resistance, and voltage? So what is the formula that relates to these two things? We did it yesterday. You'll be able to find it quite quickly. What is the equivalent resistance of the series circuit shown to the left? So this is from the lesson that I did today. So series circuit, again, you have the formula in your data book for how to figure out your total resistance for a series circuit. So gizmo warm-up. So you're going to line stuff up on here. So this is your first way. So you set this up, and then it tells you to move the ammeter next to the battery. So what is the current flowing through? So it will tell you, you'll get a reading on your little applet somewhere that tells you what is the current through it, and you should have the right units for that. Then it says based on Ohm's law, what is the equivalent resistance of this circuit? So you're going to actually use information that you have here. You're going to get your current in order to figure out your resistance, thinking about what else you need. You need battery voltage. So this one's going to be a calculation. You're not going to actually measure it. You're going to calculate the resistance in the circuit. And then it says you can calculate the equivalent resistance of a parallel circuit. So this is a parallel one, right? We have it connected in parallel using the following equation. And so this one is going to be calculating based on the resistances. So this one is based on Ohm's law. This one is based on the resistances of the circuit. So the next one, solving complex circuits. And this one does sometimes throw people for a loop. I remember that. So you're going to make this circuit. So it takes a little while. Get them all on there, a couple different resistances. So what we have is we have a couple different proportions to this. So we have some resistors that are connected in parallel. So these are connected in parallel. And then if we look, this portion is actually in series. So this and this light bulb is in series with this whole situation. So I just want to reread it quickly. So solving a complex circuit may look difficult. The crash course, she goes through one. She goes so fast, but she goes through how to solve one that's way more complex than this, that you need to kind of start with your the resistance of your parallel portions and make them into series, and then you can calculate it from there. So she goes through one super fast, but like I'm saying, it's so complex, so it seems super fast, but it should give you an idea of how to approach this one. I think that's in 30, so Crash Course Physics 30. She goes through one, so you can kind of see it. So we have light bulbs and different resistors or appliances or whatever hooked up in series and in parallel. So question 1 says, use the gizmo to create the circuit shown to the right. Next, find the equivalent resistance of the outlined parallel component. So this is the outlined parallel component. So you're going to use your parallel resistance, which is this portion here. Can I highlight? This is the formula that you're going to use to find out what's dotted around here in red or on yours in black. So calculate the resistance of this parallel component. That's what this blank is for. It says, now you found the resistance of the parallel part. What do you think you'll do next? Well, just read the next line if you need to. And it tells you to add up each part of the circuit to find the equivalent resistance of the whole circuit. So now, once we've calculated out the resistance of this parallel circuit, we can consider this 10 ohm resistor, this 15 ohm light bulb, and whatever this parallel circuit is to be in series together. That you have one thing here, you have a second whole thing right here, and you have a third thing. So then you're going to use your series calculation. So that'll give you that calculation, and then it says remove the battery, connect the two parts of the ohm meter to the ends of the circuit where the battery was attached. What is the resistance? So you'll do that one and you'll look at what the ohm meter says. Okay, this isn't so bad. I'm getting close. Okay, so the next one, it's asking you, what do you expect the total current to be for this circuit? So don't just give me a guess. Think about a calculation that you know. If you change the battery voltage, you know the resistance, you should be able to calculate out what the total current would be on this circuit. Then check your answer by placing the ammeter on the circuit near the battery. So you should show me, I know you don't have a ton of room here, show me what the calculation is that you did it. Don't just give me your ammeter reading, show me the calculation that you did for this. Question 6. So you can use Ohm's law to calculate the current and voltage through each component of the circuit. Recall that the current is the same through each series component, but gets split up in the parallel section of the circuit. So what is the voltage across the first 10 ohm resistor? So how can you calculate voltage? Again, related to the resistance and the current. What is the voltage across the middle parallel section of the circuit? So again, what you need to think about is looking at your voltage divided by your resistance is equal to your current. And what is the current in each branch of the parallel section? So thinking about, oh, sorry. I was like, what is this one? But you're still using the diagram from the last page. So looking across the light bulb, the 20 ohm resistor and the 10 ohm resistor. What is the voltage across the last 15 ohm light bulb? So again, thinking about the calculation that you need to use for each of those. Next one. Whoa, again, complex. So this is getting more and more. So we have parallel circuits kind of galore through it. So with this one, what you kind of need to do first is these two small boxes. So this small box and this small box. So you need to figure out the resistance of each of those independently. Still probably won't let me write on here. No. Maybe actually, sorry, I'm just going to copy this to Smart Capture. Oh no, Screen Capture. This might make a ridiculously loud noise. Okay, so now I can write on it. This is nice. So what you need to do with this one is figure out the resistance of these portions. I need yellow. No, no yellow. These portions first. So again, these are connected in parallel versus this and this, and versus this and this. So you need to figure out your resistance of each of those. So this is, I don't know, we'll call this 1 and 2 first. So you need to figure out the resistance of 1 and 2. And then what you need to figure out is, sorry, just let me process how I would approach this. Then what you need to do is figure out this whole thing in series. So then you need to figure out 3 and 4. And then you need to figure out your resistance of this whole thing, again, in parallel. So you need to break it into small components. Again, the one that she does is complex like this. So you can see how she kind of breaks it down kind of from parallel to things that are in series, on and on until she's kind of accounted for the entirety of it. And then, yep, so that's what that one is. So that one's complex. So again, let's do different colors. Let's go back. No, isn't working. Of course it's not. There we go. So do this one first. You can, let's do, I don't want to change it. I was going to do this one second. Then using what you calculated from 1, figure out this portion. So we'll call that 3. And then using what you calculated from 2, do 4. And then using both of those again, they are in parallel. Using that. Well, can't see anything up there. So that is kind of your final portion, is figuring out those two in parallel. So again, these are series or parallel and series. I promise that's a series. And then this one again is in Be a Friend, parallel. All right, so holy moly, I don't think the last couple are too complex, so I'll be just about done. So this one is fuses stuff. So I've already talked about it. It prevents kind of an overload, and it's built. I've already answered one of the questions I see now. Oh, here we go. So based on the number on the fuse, what do you think the maximum current is? So just looking at what pieces of information you have, so it's kind of a guesstimate here. What is the maximum battery voltage that you could use? So it says use Ohm's law. So you're going to have the maximum current. You're going to have oh, sorry, yeah, you're going to have your maximum current. You're going to have your resistance, sorry, there we go. So you'll be able to calculate out the maximum voltage that it could be. So reading on an ammeter, test it, see what happens. What's the maximum voltage now? Again, that's a calculation you'll need to do, and test it out. So this page should be a little bit easier, just follow the instructions. Build a parallel circuit. So click the switch to turn on the first appliance, turning on the second appliance, turning on the third appliance, so they all have a resistance of 100 ohms. These ones, again, what do you think will happen? Turn on the switch. What's happening? Yeah, but this last page should be pretty easy too. And again, think about circuit breakers. It's nice, I just talked about it, so you can rewind and listen to me jabber on again. Okay, so that's the assignment for advanced circuits. Again, if you get hung up, send me an email and we can go through a question together. We can log in and share a screen or something like that, and think about what you can do. So thanks for watching. Play around with the apps, and we'll talk to you later.